So now let's proceed to this measure theoretical proof of the existence and uniqueness of Hart measure. So let me start by giving out a rough idea how we construct such a left invariance measure. So first of all, the idea is the following. So let's start by looking at a K, suppose it's compact. And then we want to kind of measure how big this K is. So you have a K here. By measuring how big it is, well, what we can do is we can use some open sets to cover it. Okay, so we can do some open cover. So let's say that E is inside V, where V is open. Then we can consider how many copies of this V I need. Okay, by that I mean, so first of all, because K is contained in the union of the XV, where X is inside K, and by its compact, there exists a finite subcover, so there exists X1 up to Xn, so that your K is contained inside this finite Xi times V. So each of these little ball is centered around some Xi, and you measure how many you need. And roughly the idea is because of you want to have something that's left invariant. So each of these xiv's, so I going from 1 to n, that's the same size as v, okay? So the size is kind of fixed. So by, let's say, k can be covered by n of them, then the volume or the size of this k is roughly n times the size of v, okay? So that's kind of the idea. Of course, there are going to be overlap, and you need to approximate better and better as v goes to 0, okay? So that's kind of this how many copies of V can cover this K that give you kind of the relative size of your compact set K relative to this open set V, okay? So let's write down this definition. So first of all, let's put this idea into a definition. So let's say for every K that's compact, and let's say for every V is open, and let's define the following. Let's define K over V. Well, let's use this notation. That's basically the minimum number of these open cover you need. Okay, so it's the minimum number of n where there exist n elements x1 up to xn, so that K is contained in this finite union. Okay, xi v I going from 1 to n. Okay. So by the compactness, we know this is certainly less than infinity. So it's just a matter of which one is the minimum. Okay. So of course, the idea hopefully is that when v goes to 0, so as v becomes smaller, this approximation becomes finer and finer. So eventually, this gives some left invariance measure. But now we do have one problem. If you notice, just following this definition, this one will go to infinity if v goes to 0, okay, or goes to the identity, because as v becomes smaller, then you need more and more of these copies of v to cover your k, okay. So you need something to normalize this whole thing. So basically we need to normalize it with some value, okay. So maybe let's just fix some k. So let's say fix a k0. Let's say it's compact. Without loss of generality, let's assume that the interior of this k0 is non-empty. Okay, we can always pick one because our group is locally compact on Hausdorff. Okay, so we need to divide this kv with respect to this k0v. Okay, so k0v is kind of the normalizing factor. Okay, so let's make the following definition. So let's define for each v open. Let's say, well, E open neighborhood of the identity. Let's define the following. Let's define the mu of V. Okay, it's going to be a map from the set of compacts. Let's use this curly K as the set of compacts to the reals. Okay, so if I give you a K that's compact, well, I will map it to the following. So first of all, I have to measure how big it is using this open neighborhood of identity. And I need to normalize it using this fixed k0, okay? So as v goes to small enough, then this k0 K0 over V, that's also going to be infinity. It's also going to be big, but you normalize it, so you get something that's hopefully that's going to be finite, okay? So that's kind of the idea. All right, so I want to, first of all, let's prove that this mu of V we define is actually not going to be infinity, okay? So let's make the first claim. Let's do the following claim. So I want to show that, first of all, this mu of V is going to be of some k is going to be less than equals to the following, less than equals to this index by the k over the interior of this k0, okay? So in other words, I just need to show that this index k over v is less than equals to the product of k over interior of k0 multiplied by k0 over v, okay? So this is fairly simple to prove actually. So let's do the following. Because let's just make some assumption. These are all integers. Let's say this is n, this is equals to m. Okay, so first of all, because you have k0 over v, the index is m, so there exists say y1 up to ym inside your group G, so that you can cover your k0 by m of these translations, so say yj of v, where j going from 1 to m. Okay, so k0 can be covered in that. And similarly, you can cover your k by the interior of k0, so there exists say x1 up to xn inside G, so that your k is covered by the following. So union of I going from 1 to n of these xi translate the interior of k0. But you can cover it up further by this k0. Okay, you don't need the interior, so that's covered by the union I going from 1 to n of xi of k0. And k0, you can replace it by the cover using v, so this is contained in, you do the calculation, so this is I going from 1 to n, and you can just multiply everything inside, so it becomes j going from 1 to m of the xi yj of v, okay? So you treat xi yj as a single element in G. So you see your this v, you have a cover of n times m of these neighborhoods, okay? That's an upper bound. Of course, it's going to be less than that. So this proves that your k, the index k over v, is going to be less than equals to n times m. Okay, you need at most that many. Okay, because it can be achieved. All right. So I just want to point out one quick remark. Because you basically do the same argument, so as long as the interior of your k is non-empty, then what you can show that the mu v of k, it also has a lower bound. Okay, you can reverse k0 and k. You can show that it's bounded below by this constant k0 over the interior of k. Okay, it's essentially just the same proof. All right, so I want to, before we move into the construction of the Haar measure from these mu v, let me briefly talk about their properties. Okay, so I want to show the following proposition. So first of all, I want to show that they are monotone. So if I have a k1 containing k2, then first of all, this index k1 over v is going to be less than equals to k2 over v. And because we're normalizing everything by k0 over v, so we have mu v of k1 is less than equals to mu v of k2. So that's kind of what we expect. And second, I want to show that they are actually sub-additive. So if you want to have, let's start with the index first. So suppose we have a k1 union k2 and want to look at the index over v. It's going to be sub-additive, so it's less than equal to k1 over v plus the k2 over v. And you can basically divide this whole thing by the index of k0. So equivalently, you can say that mu v is also sub-additive. So if you have union of two compacts, is less than equals to mu1, mu v of k1 plus mu v of k2. And finally, I want to show that if you have two compact sets, and if they're kind of separated enough by this v, then it's actually going to be additive. Okay, what I mean is that if you have this K1 times V inverse is destroyed from the K2 times V inverse, okay, then you have the following. You have that everything is going to be additive, okay, so you actually have K1 union K2 over V is going to be equal to the sum, okay, so it's additive now, okay, and of course you can translate in terms of mu V, so mu V on these K1, K2, they're going to be additive, okay. All right, so the proof is kind of trivial. So for the first and the first two, you can just convince yourself because the first one, a cover of K2 is a cover of K1. Second one, you can basically union up two covers of K1 and K2 to get the cover of K1 union K2. So I'm not going to prove those. So let's just say 1 and 2 are trivial. The only thing is probably the number 3. So it's also kind of trivial because of the separation. So suppose you have some cover, let's say K1 union K2, you cover it by some Gi times V, where I go from 1 to N. And because you have these, the K1, K2 are kind of separated by this V, then suppose you say, if I have a Gi, let's just say some GIV, if it intersect K1 is non-empty, and if it intersect K2 is non-empty, then basically what we can show is that there exists, okay, so there exists some this Gi times some, say, X inside V, that's going to be inside K1. So in other words, this Gi is basically inside, you translate on the right by this X is inside V, so G is inside K1 V inverse. And so I should say the first one implies that, okay? So the second one will also implies that use the similar argument, the Gi is inside K2 times V inverse, but this is a contradiction. These two are kind of separated. Their intersection are the empty side, so you can't find it. So in other words, so if you have number 1 and number 2, so each of these GIV either intersect your K1 or intersect your K2, well, so you can separate them, okay? So n of these translation of neighborhood, you can separate them as covers of K1 and covers of K2. So you can convince yourself that implies the other direction. So if you consider the covering of K1 union K2, that's going to be greater than or equals to the other one, okay? So it's going to be subadditive, well, superadditive. And the subadditivity is followed by number 2, so we get equality here, okay?